Okay, cool.
Yeah.
Hello, yeah. Okay, all good. Okay, cool. Hello everyone. I'm very excited to see all of you. So it's Chen Hao from PingCAP. So I'll be the host today. So today we have Professor Ramzi Apasi Duso and Yifan Dai from the University of Wisconsin Madison and Qi Xu from PingCAP. So TiKV is an open source distributed and transactional key value database. It is a graduated project of CNCF. It is also the storage engine for TiDB. So Qi will discuss the TiKV's evolution and its ongoing architecture changes. He will also discuss the collaboration between PingCAP and the computer science department at the University of Wisconsin-Madison to explore using Symbiotic cache to optimize distributed key value stores. Then Yifan will explore Symbiosis in more details. He will present the design of the system, some initial experimental results, and how it might be helpful to TiKV. Okay, so let's start with Qi. So Qi is a software engineer at PingCAP. He works on TiKV. Before Qi joined PingCAP, he worked in the Alibaba Cloud Storage team and Microsoft Office 365 team for more than 10 years. Okay, let's welcome Qi.
Thank you, everyone. Thanks, Chen Hao. Yeah, I'm Qi from PingCAP. I'm a software engineer in TiKV team. So today, I'd like to share with you a little bit about the TiKV's evolution. So actually, TiKV has a lot of change since it's released. And today I'm only talk about a few parts of the evolution. So we'll focus on the storage part. Okay, so here is the agenda. So we'll briefly talk about what is TiKV and the evolution of TiKV and the challenges and the potential improvements of TiKV and the area where we can collaborate with Professor Ramsey's team to improve the TiKV's the performance in the future. So, okay. So what it is the TiKV? So it's TiKV is a distributed transactional KV service. From its core, it consists of two parts. One is the distributed storage. So that storage provides like no single point failure, horizontally scale out, high availability and high performance. And on its top, it provides the transactional APIs to provide the strongly consistent data consistency across the replicas, and then to serve the TiDB's need as a storage engine. So, and today for TiKV, it's used by a few customers like TiDB Cloud and the Daily Motion and the JD Cloud, and also the Zello Pay. And that's a few more. Okay, so TiKV is an open source project, and you can see you can visit its source code from the GitHub, and also we have there's a application called OSS Insights. You can check out the TiKV's some fun interest facts, like how many stars, like commitments, issues, this kind of thing. And yeah, we are honored that developers like our product, and we continuing see it get more and more popular in the community. Then we talk about its architecture. TiKV is a like horizontally scalable KV service. So each TiKV node, it has hundreds or thousands or even more regions. Here, region is a scalable unit. It's kind of the logical partition. So in other system, it's always sometimes it's called partition, and each region, it has several replicas in different TiKV nodes. And to ensure the data consistency between the replicas of the same region, we use the raft protocol to enforce this data consistency and the replication. And on the top, we have the placement driver cluster. So this is the components that's responsible for the TiKV's data balance and also the load balance. So basically, it wants to ensure each TiKV have the roughly similar size of data and have the similar read request or write request. And on the top, we provide a gRPC layer as the API that our clients can call to do the job. Let's take a close look at the TiKV component in a logical way. So it on the top is a TiKV API and the coprocessor API. TiKV API is for most for the transactional API like read, write, and maybe delete. And the coprocessor API is more about the some specific query like when we want to do a range select or we want to do an aggregation. Some of these operators are pushed down to the TiKV for the better efficiency. And underlying there's a transaction component. This is where all the like MVCC logic or the two phrase commitment or one phrase commitment, those logic is implemented. So it basically provides the transactional semantics to TiDB. And under the transaction component, there's a raft store component. It basically provides the abstraction of the distributed storage. And the bottom one is the RocksDB. It is a local storage engine that initiates from the Facebook. Okay, so now I want to highlight some key facts of the TiKV's storage. So first, currently the sharding is done automatically, so by the PD. And the shard, essentially the region size is 96 megabytes by default. And we usually don't recommend the customer to change it as it's be tested as a trade-off between the performance and the scalability. And also, so we have the called multiple raft group to handle the regions parallelly. So basically, the operation on between the regions, they can be handled parallelly, but the operation within the region, they are being handled sequentially according to the time step. And for the data storage, we have one RocksDB instance. That's a one RocksDB instance for store all the data in the one TiKV node. And we have one raft engine instance to store all the raft log in the one TiKV node. Okay, so I'd like to briefly introduce about the multi-raft group and how it works. As we mentioned, the data are partitioned by the regions, and each region is a one raft group. So we have the two thread pool to process the data. So one thread pool we called is a raft FSM. That thread pool basically handles the user's traffic and then pull those traffic into the raft log, into the raft engines. And another thread is we call the apply FSM. That one is to basically pull the logs from the Raft log and then apply them to the RocksDB. And each region, the data are processed in the sequential order, but between the regions, they can be handled parallelly. So that's basically the high level introduction of multi-group, multi-raft groups. And there's some details such as when we do the processing to achieve the better throughput, we batch the changes from so basically we don't like get a change and then persist it to the logs directly. We batch up and until like it exceeds some threshold or there's no incoming requests in the queue. Then I'd like to talk about the Raft engine. The Raft engine is designed to store the Raft log only. Actually, before the version 6.1, TiKV used the RocksDB to store the Raft log. And but we find out that Raft log actually the access pattern is much simplified. And it does not need the full functionality of the RocksDB. And we have a chance to optimize it for this specific scenario. That's why we introduced a new Raft engine that for the purpose of storing the Raft log. So the key difference here is that first all the data index are actually stored in the memory table. So it's unlike the RocksDB. Memory table is just store a partial data, but in Raft engine it store all the index of the Raft engine's data. So this is doable because the Raft log typically is much smaller and it's a temporary and it will be discarded after the data is persisted. So the data set is smaller, and so that's why we can use the whole memory table to store all the data. And then we don't need to have multiple layers of like SST. So we simplify it, and it turns out that the result is very good, and its tail latency is reduced by 20%. And the write amplification is reduced by 40%. So what if the data scales up to 500 terabytes or even more? As you see in this picture, the data size is 518 terabytes, and it has 1.2 million regions. And in fact, in some customer, their data size is even larger than these pictures. So what will happen if the data size is close to 1 PB? So here is I listed a few challenges that when the total size is becoming very large. So the first one is there will be too many regions. So 1.2 million region is not actually the biggest number. We saw in some customers, they have 2 million regions. And each region, it not only consumes the memory in the TiKV, but to maintain the Raft group, it needs to have the heartbeat between different replicas. And also it needs to do the heartbeat from the TiKV leader to the PD. So it's quite expensive to have like 2 million regions, even if there's no traffic. The initial cost is quite large. The second challenge is that the scale speed is very slow. today, so as we mentioned, we only have one database per TiKV, and but when we scale the data, we scale one region's data for one region by region. So all the regions data are all stored in the same TiKV RocksDB instance. When we scale, we need to scan the whole database to find a specific region's data. And then we generate the SST for that region and send it to another node. Then another node will basically ingest the SST to its own local database. Here, the expensive operation is the scan. So imagine that we have 4 terabytes data. We want to move 96 megabytes data. So if the compaction is not done so if there's many like pending compaction bytes in that node, you can imagine that how expensive to scan the whole database to just find out the 96 megabytes data. So that's why, as a result, if we want to scale like 1 terabytes data, to scale out, it will take more than 1 day. And to scale in, then it takes a few hours. So it's kind of quite painful when user, for example, wants to urgently add the capacity to serve the new the ever increasing traffic, because the scale up speed is just too slow. The third challenge is that the RocksDB is not designed to like support a few terabytes data. It does not perform well in such case. One case is that if the value size is large, saying the value is 4K or even more, then the RocksDB is not perform very well, and it has very huge write amplification. The second is when the data set is large, its compaction flow will be like very large, even if the value size is quite small. This is because when we do compactions, we sometimes we have to deal with those data that actually does not have much traffic, but it did have some random write. We have to loop all those data into the compaction process. And in the real environment, it's very common that the compaction flow can be 10 times or more than the actual write flow. The third one is about the RocksDB's global logs. As we know, RocksDB has a mutex. So when you want to write the data, or you want to read, get a snapshot, or you want to do the flash, or want to do the compaction, mostly you have to grab that log. So that log, when we have so many SST files and so large data, the log contention will be very expensive. And the last part is about the write amplification, as we mentioned, because that partially because of the compaction cost, and also the latency jitter. This is mainly because we have the global logs, and sometimes if on the heavy traffic, read and write will impact each other. So we will see that the latency is not very consistent on the heavy traffic. So to solve these challenges, we've made a few improvements. The first one, so to address the too many regions, we introduced a feature called hibernate region. So the idea is that for those regions that is idle for some time, so we can put it in inactive mode. When it's in active mode, then its heartbeat interval will be extended from typical like 3 or 5 seconds to like 15 seconds or even more. So by this way, we can reduce the heartbeat cost of the hibernate regions. And for those hot regions, it still have the frequent enough heartbeat to reflect the changes quickly. So this one, basically, we can reduce those idle regions CPU and CPU cost to both TiKV and the PD. So to address the large value data in RocksDB, we propose a new, basically a new database based on the RocksDB and inspired by the Whiskey. So essentially, it separates the large value from LSM tree. And it turns out that under large value scenarios, it has 3x performance write throughput when the value size is 1 KB or more. So this is the improvement to address when the value size is large. The final one is, so we want to completely address the performance, the scalability issue. As we talked just now, that the hibernate region can mitigate some problem. But when in some cases, like when we need to restart the machine or some nodes gets down, all the hibernate region will be reactive. So to do the leader election and some other work. So it's not completely solve the too many regions problem. So to fix that, we introduce the concept of a dynamic size of region. So essentially, the region size is not fixed by 96 megabytes, but now it can range from a few 100 megabytes to maybe 10 gigabytes. So according to the traffic pattern. So with the larger region size, we can effectively reduce the region count. And also to address the slow scale speed, we introduced a new mechanism for the storage. So instead of we have a unified RocksDB instance, we want to have one dedicated RocksDB per region. So by this change, essentially each region has its own RocksDB physically instance, and each region they are separated with each other. So that means when we do the scale out or scale in, we just copy the files from one machine to another machine, and it will not impact other regions' normal operation because they are totally different database. So there's no global mutex anymore. By this basically new change, we see that in our alpha version of the new architecture, we see the scale in speed can be improved by like fivefold to tenfold, and the scale out speed can be improved by 5 times. And also for the some specific workload like the bulk write, its throughput can be doubled. And also the compaction flow can be reduced by 70%, 75%. And also because there's no global mutex, it provides more predictable throughput over time. And last but not least, because it's physically isolated for different table, database, and the user, so theoretically we can implement some features like bring your own key to do the encryption. Because imagine that each database may owned by different team and they want different keys. Before this feature, all the database, they are encrypted by the same key because they are all mixed together. Now it's actually separated, and we can have different encryption mechanism or different key to protect them. So it's kind of a side benefit of this feature. Okay, so now let's talk about the new challenges. So the new architecture indeed can solve some problem, but it also unfortunately have some new challenges. Here I like to highlight a few of them. First is it has too many memory tables. Originally, one instance we can have 5 memory table or maybe 10 at most. So its memory consumption is very limited. Now we have maybe 1,000 RocksDB instance, and each instance have maybe 2 or 3 memory table, and it still adds up, and it consumes a lot of memory. And the second is so when the memories, if the size, if it's too small, saying each memory only have 1 megabytes data, then we will have too many L0 files, because too small L0 files and too many L0 files, they will trigger the too much compaction, and this will lead to very poor performance. But if we keep the memory size fairly big, then we will eventually hit out of memory. Saying we have 100 megabytes memory table size. Imagine we have 1,000, so it's easily can have OM. So to solve this problem, we may need some good strategy to proactively flush the memory table. So either based on size or based on the age, or maybe we need some more intelligent strategy according to the real traffic. So this is one of the area that I hope we can work with Professor Ramsey's team to figure out like better strategy to achieve the balance of the performance as well as the memory consumption. The second challenge is about the compaction scheduling. So before a single RocksDB instance, the compaction is triggered when a certain condition is met. For example, the L0 file count, or maybe the specific levels size hits the threshold, then it will trigger the compaction. Now we have so many RocksDB instances, and each instance, if they still use the same strategy to trigger the compaction, then we can see that the compaction flow is essentially is not stable, and it has so many spikes. And when each spike happens, it basically bring down the block hash hit. And then the whole the user's traffic will see the QPS jitter. It's essentially it's not very stable. So we need some like global compaction scheduling, so that we may do some first we may want to flat the compaction flow. We may need to limit the compaction flow's throughput. And also we want to do the compaction smartly and based on the traffic pattern. For example, if this database does not have much read, then maybe it's affordable to have it not compacted for now, and prioritize for those very hot DB's data. So we can compaction those hot DB first, something like that. So this is also, I hope we can work with Professor Ramsey's team. The third part is about the size inflation. So because multi-RocksDB instance, it has much more L0 files, same as a memory table. So L0 files, each RocksDB will maybe have 2 or 3 L0 files, but when we have 1,000, it adds up. And those L0 files, they are not compressed. This is because L0, typically when we want to read the data, it's quite expensive to parallelly process those L0 files. And we don't want to add more burden to do the decompression. So L0 typically is compressed, is not compressed. Now, because we have much more L0 files, the size, the disk size will be inflated because of that. And so the solution maybe is we may need to smartly compress the L0 file also based on the traffic. So saying those traffic, if those database does not have much read traffic, maybe those we can do the compression on those database. The last part is the memory, essentially the memory optimization. So today we have 3 major memory consumers. One is the memory table. The other one is the block cache. The third one is the OS 5-page cache. So given the limited memory size, how we allocate memory to those 3 different consumers to achieve the best performance? And can it be automatically tuned dynamically by the real-time traffic? So I think this is the very interesting area that I think I want to work with Ramsey's team to leverage their research to improve TiKV's performance. Yeah, that's all my introduction about the TiKV's evolution, especially the storage side. So yes, if you have questions, feel free to ask.
Okay, thanks a lot, Chi. So from his talk, I believe you know a lot more about TiKV. So there is a question. So what will the impact be if we use a large region size in TiKV, for example, 1 GB?
Yeah, it's a good question. So to support the large region size, we did a lot of work. So one side effect of the large region size is first, when you do the query. So today the parallelism is determined by the region. So in the TiDB side, if the query is in one region, then it will only have one thread to process it. So it will not split so the region size, if it's very big, it won't split this request to multiple small tasks. So it will impact this scenario when the region size is big. And the other impact is that, so when the region size is large, it will be more challenging to do the load balance and more expensive, because when PD moves data, it moves the whole region's data. So when the region size is large, it will be more difficult and sometimes more less efficient to do the load balance, because you have to move the whole piece of the data. So to fix that, we introduced the concept of the bucket. That is a new parallelism unit in TiDB, so that when we serve a large query, we split the query by this bucket. This bucket is small enough so that we can maintain the same performance as the small region. And to achieve the load balance, so we also leverage the bucket to identify which part is the hot with a hot data range, and which part is cold. And we basically split those hot data range into its own region. And so basically, to achieve the load balance, we first do the split to make the data small enough, and then we move the data to other nodes to achieve the load balance. So because we in some case we want to achieve the traffic balance, right? This is called the load balance. This we need to identify which data range is hot and which data range is cold, and distributed them equally. So yeah, this is the work we did to mitigate the large region size side effect. Yeah, hope I answered your question.
Yeah, okay, cool. Thanks, Chi. Okay, so no more question here. So we'll now move on to Yifan. So Yifan will explore the symbiosis in more detail. He will present the design of the system and some initial results. So Yifan Da is a fourth-year graduate student at the University of Wisconsin Madison under the instruction of Professor Ramsey. He is generally interested in file system and their interaction with the applications. So let's welcome Yifan. Yifan, it seems like you muted yourself. Yeah, cool.
I'm on mute now.
Yeah,
can you hear me?
Yes.
Okay. Thank you very much. Thank you for the introduction. And hello, everyone. I'm Yifan Dai, a fourth-year PhD student in University of Wisconsin Madison, advised by Professor Andrea and Ramsey Aparti-Dassault. I'm going to present Symbiosis, a framework for the application and kernel cache coordination. So nowadays, large-scale database systems such as our TiDB and MongoDB, MySQL, use storage engines to interact with local storage systems. TiDB uses RocksDB, MongoDB uses WildTiger, and MySQL uses InnoDB by default. These storage engines have their own caches within the application, but there is also another implicit caching layer in the kernel. This application and kernel two-layer caching is common, as some storage engines like WildTiger and Cassandra by design rely on the kernel cache to cache compressed data. And sometimes in virtualized environments, we just have no control but to accept this underlying caching layer. So correspond to the last talk, in this talk, we use the application cache to refer to the block cache in the last talk, and the kernel cache to refer to the kernel page cache, the OS page cache. And then data compression adds to the complexity. Data compression is commonly used in storage engines to trade more computation for much lower device I/O. In common settings, compressed data are stored on disk and cached in the kernel cache. When accessed, they are decompressed and then stored in the application cache. The application and kernel cache share the same resource quota, so there's the problem of cache size partitioning. There are challenges in this cache structure. So first, the kernel has its complicated and closed nature, leaving us with very limited control over the kernel cache. For example, we can only control its size, which is adjusted indirectly by controlling the application's memory consumption. Then it comes to the focus of this project, the optimal cache sizing problem between the application and the kernel cache, which turns out to be surprisingly hard. We use a simple experiment to show the complexity here. We compare two different application cache sizes on LevelDB. One size is LevelDB's default cache size, 8 MB, which is very small. And the other one is 1 GB, which uses all the available memory in our setting. We run a uniform workload with two dataset sizes, 1 GB that can be held in memory in its decompressed form, and 2 GB, which can be held in memory when compressed, as the compression ratio we use here is 0.5. We use the term dataset size to refer to the decompressed data size in this talk. The graph below shows the results. The y-axis is latency normalized to the lowest item, and the number on the bars is the absolute latency. When dataset size is 1 GB, the 1 GB application cache can hold all the data, saving the decompression cost, and performs better than the small 8 MB application cache. But when the dataset size is 2 GB, using a minimal application cache gives most of memory, gives most of memory to the kernel cache so that it can hold all data in its compressed form. while a full application cache now incurs a large number of these accesses, causing performance drawback. So we can see that even in this simple experiment, no single cache size performs well in both conditions. While it is a hard problem, there is also a large potential gain just by having the right cache size. So in the 2 GB dataset size case, the gain is larger than 7x. So we build a framework, Symbiosis, to study the coordination between the application and the kernel cache. One of its components is an offline cache simulator. We use it to study the effect of various factors on the optimal sizing problem. I will describe its design validation and a few interesting results. Then I will talk about the online adapter that can automatically resize the application cache to a better value during runtime. I'll describe its design, show some preliminary results, and then the challenges we're working on. The cache structure in our offline cache simulator looks fairly simple, but the challenge of the offline cache simulator is that we need to correctly implement the related kernel features to have an accurate simulation. One of the important feature is read ahead. So there are two kinds of read ahead: the access-based read ahead, which is trivial, and a more complex context-based read ahead. The bar below represents contiguous pages of a file, and the black blocks represent the pages that already resident in the kernel page cache. When one first accesses a page and then accesses the next page as shown in the bar, the kernel treats it as a sequential access and read more pages at the second access. This is the access-based read ahead. The context-based read ahead is a bit more complicated. In the second file, there was already some existing pages in the page cache. When one accesses the page next to the recent resident pages, the kernel recognizes that, okay, there are contiguous resident pages before the target. So it also triggers read ahead because it may be an interrupted sequential access. This contextual read ahead is the key to make the kernel read ahead algorithm suitable for almost all workloads, including random ones, and under almost all memory constraints. So basically, we want to have more read ahead when we have low memory constraints, and we want to have a low read ahead rate when we have higher memory constraints. So when the memory constraint is high, the possibility of having resident neighboring pages is low. So the number of read ahead is also low, and vice versa. And this is how this contextual read ahead adapt to memory constraints. Another kernel policy we want to pay attention to is its eviction policy. Essentially, it's a 2-queue policy, and we carefully follow its queue balancing and promotion algorithm. We have an eBPF-based kernel stats collector that can trace kernel function calls and derive the corresponding statistics. There are functions indicating kernel cache hit rates and other more detailed statistics like the number of read aheads and evictions. We use the tool for early stage case studies and validation of the accuracy of the simulator. We also find a bug in WildTiger's eviction policy using this tool by observing abnormal kernel cache hit rates. The bug is reported to the developers and recognized as a major bug. Then we talk about the effect of each factors that affects the optimal cache sizing problem. We have done a thorough study of various factors. In the real world, we have different resource constraints, machine specs, application characteristics, workloads, and more. We abstract their influence into the factors in the middle column. For example, the resource constraints corresponds to the available memory, and the machine specs corresponds to the kernel cache miss rate, which is mainly the device access latency. We also study those factors under different workloads. In this presentation, I will talk about the effect of dataset size and application cache miss cost, and focus on the uniform workload. In a uniform workload, we can find some simple and interesting patterns. For example, if we describe latency, which is y-axis, as a function of the kernel cache size, which is on the x-axis, there would be always two possible local minima, one at kernel cache size being 0, and the other at a smaller value of the available memory and the compressed data size, which is the dataset size times compression ratio. When the available memory is less than the compressed data size, the curve will look like the curve shown here. The optimal cache size takes place at either side of the domain. When the available memory is larger, by larger than the decompressed data size, the curve looks like the second curve, where at a point in the middle, the kernel cache can already hold all the compressed data, and further increasing its size simply wastes memory and increase the latency. So to understand the two kinds of curves, we can think it intuitively that the optimal cache size takes place either when we give all the memory to the application cache, which corresponds to the 0 local minima, or we give all the memory to the kernel cache until it can hold all the compressed data. Any value in the middle would cause duplication in both caches, since we cannot affect the admission policy of the underlying kernel cache. Which local minima is a global minima depends on the factors we study. Next, I'll show the effect of application cache miss cost in the uniform workload. We fix all the factors. The intuition here is that a larger application cache would be favored if its miss cost goes higher, or we just would pay the higher cost. The graph below confirms our intuition. It shows that shows latency with different kernel cache sizes and application cache miss cost. We have the latency at the y-axis and the kernel cache size at the x-axis. We have several lines. A lighter line means a higher application cache miss cost. The triangles in the line indicate the best kernel cache size in this case. So we can see when the miss cost grows, the best kernel cache size shifts from the compressed data size to left to the 0. The effect of dataset size is a bit more complicated, as it changes the compressed data size, thus changing the value of one of the local minima. The intuition is that a larger dataset size favors a larger kernel cache, since it can hold more data in the compressed form and provide a higher hit rate and lower device access. The graph below shows the latency with different dataset sizes, a darker line indicating a large dataset size. So when the dataset size grows, we can see that the best kernel cache size shifts from 0 to the compressed data size in those middle lines, and then to the memory size M in those upper lines. When it further grows, the latency difference between the two local minima will be very small, as most of the access will be misses anyway. Then we talk a little bit about the non-uniform workload. When we have non-uniform workloads, the patterns in uniform workloads are gone. The graph below shows the latency with different dataset sizes, which is just like the graph on the last page, but under an 80-20 skewed workload. It is hard to recognize any pattern about the best cache size in the graph, and we can only get the best cache size through constructing the latency curve with simulations of different sizes. So this leads to our idea of a simulation-based online adapter. The goal is to automatically resize caches according to the workload. We add adapter as a built-in model into the storage engine application, and it collects the real workload traces, run simulations of different cache sizes in its ghost cache, and outputs the best cache size candidate. The ghost cache has the same cache structure as the real system, but only stores keys to simulate cache hits and misses. It simulates with the current workload on different candidate cache sizes to see which one yields best performance. And then we have another evaluator to see if we really want to adapt the best candidate size to the real system. We build the adapter into LevelDB and conduct a preliminary experiment. We run a uniform workload whose dataset size is equal to the available memory, which means that having all the memory for the application cache can hold all the data and provide the best performance. We compare the adapter with the default configuration of 8 MB, a very small application cache. The result is shown in the graph below, where the y-axis is latency and the x-axis is the workload progress. The orange line is default configuration, which keeps a latency of 7 microseconds. The blue line is our adapter, which starts from the default cache size, runs and finishes the simulation at around 20% of the workload, changes the application cache size to have all the available memory, and then achieve a latency of around 4 microseconds after the cache warms up. There are still many problems to solve here. We are working on a more simplified and efficient ghost cache simulation to reduce the overhead while trying to maintain a high accuracy for most workloads. We're also working on a mechanism to detect arbitrary workload changes. While we build our adapter into LevelDB, this idea should apply to any storage engines with data compression, like RocksDB and Cassandra. This is the end of my presentation. Thank you for listening.
Okay, thank you so much, Ivan. Okay, cool. Let me see if there's any questions. Seems like there's
actually
no question.
I have a quick question. This is Liquan from PingCAP. Before you start working on this problem, what are in your research? What are other like solutions like to make this like cache more effective in your like investigation?
Actually, we kind of run into like when we start the cache study with some case studies, we quickly find the problem that, okay, with different settings of application cache size, the performance can be very different across different workloads. So we just decide that, okay, this may be maybe a very straightforward but effective problem to work on. So yeah, that's kind of the first target in my study.
Yeah, but I could add to that, if that's okay. You know, one way to look at this, there's a broadly in the systems field, as you know, there's a bunch of interest in using, you know, machine learning or other similar techniques to automatically configure or tune complicated systems. And, you know, in any at 10,000 feet, this is a tuning problem. So I think the question that we're exploring, maybe in a meta way, is can we, with a more application specific knowledge, like that we know what exact problem that we're solving, build a better configuring approach than we would with something that's kind of a black box, machine learning driven approach or something like that. So I think that's one kind of thing that we're just generally interested in. I guess a second maybe engineering solution is simply to, turn off a kernel caching and always handle everything in applications. But I guess that we convinced ourselves over time that, especially when you're running in cloud scenarios and things of that nature, that you don't always have control about the layer below you, right? So it maybe that caching's happening underneath you, whether you want it to or not. So we convinced ourselves, I think, that 2 layers of caching are not going to be an uncommon thing, and it'd be good to figure out how to make those 2 layers work better together than they might otherwise. So I don't know if that answers your questions, but certainly
Yeah,
that's what
that actually answers my question. I think definitely this is a very interesting problem to do, to work on, and also this is also a tuning knob for us in the TiKV and TiDB setup.
Yeah,
because occasionally, and not only in TiDB, maybe any like LS M-tree based system.
yeah.
In my previous company, we actually try to play with whether we should use kernel cache because you can cache more in a compressed version, or we should use more like application level cache. So this is definitely a very interesting problem to explore. If there's a more intelligent way to configure those values, I think that can definitely simplify the application or the system builders work.
Yeah, great. Now I look forward to connecting with
I have another question. So now here we only have a kernel cache and the application cache. So how about like inside the application cache, we may have a multiple layer. So for example, RocksDB, we have memory table. Arguably, we also can think it's a cache, and the block cache, right? So how to allocate the memory between memory table, block cache, and the kernel cache. So is this system can be extended to such scenario? So basically, we add more component cache. So can it tune the
Okay. I can hear you clearly, but I think I understand your problem. I think that for now, so this cache project, I'm only working on read-only workloads. So we only have one kind of application cache, which is the block cache in the system. So like when we extend the study to to have also write workloads, then the main memory table stuff can add into the application as it helps better in write workloads, if I understand it correctly, right? So I think if we follow this the mindset of this project, it will be that we have another competitor for memory usage, and we have a different kind of workload, which is a write. We still profile or simulate through the current workload, the real workload, to see, okay, which size configuration can help the current workload and gives the result. This is some of my earliest thoughts, but yeah, there would be other specific problems like the search space would be larger. We only have one variable in our study, that's the application cache size, and the other one would just be determined by the rest of the available memory we have. So if we have 2 variables, the search space would be squared, right? And yeah, there are problems remaining, but follow this the mindset of this project. I think we have the potential to deal with this problem. Thank you.
Okay, so thank you.
Okay, cool. So is there any more questions? No. Okay, cool. So thank you very much for Ivan, and thank you very much for Professor Ramsey. So I'll be sharing my screen for okay, cool. So if you would like to join TiDB community, here's the TiDB Slack LinkedIn page. You can also try TiDB Cloud for free. So we currently have serverless tier. I believe it's one of the earliest pioneers in the serverless tier, in the HTAP serverless tier for cloud database. Okay, cool. That's everything for today. Thanks everyone for coming. I'll be seeing you next time.